a voltage amplifier, might look like this. You know, I write it various different ways, show it different ways, because they're all voltage amplifiers. And you need to get used to looking at the topology and understanding what it is, not the actual letters and names of things. Oh, crap! How am I going to get up there? Huh. So by the location of resistors and sources, you can understand what they must be and shouldn't be confused from that point. So we've got a source voltage, Vs, and a source resistance, Rs. And we have a input resistance. This is on the amplifier. And there's an input voltage on the amplifier. I'll clarify that in a second. And then we have a voltage-controlled voltage source which has a gain, the open circuit voltage gain, AV0 we might call it, times VI. And VI is this voltage we see across here. So magically it comes over and powers this voltage source. It gives a value times the gain. And then we have an output resistance to the amplifier. And we can show the load. And then we have an output voltage. So this much is the signal source. The signal generator, if it was in the lab. And this is whatever is on the output. We usually just talk about the load and don't really worry about it too much beyond that. And this is the amplifier right here. And I might add in a ground. It doesn't really have to be there. It's this ground is a common reference. Oh, I shouldn't use that color, should I? I can't undo. I don't want to use that color because I've just written ground at the ground. That color. It's a common reference, and I don't want to use red for ground. This common reference is reference to all these voltage. It's a reference to Vs. We know that Vs is the voltage from here to ground. We know Vi is the voltage from this node to ground. This voltage source supplies AV0 times Vi from this node down to ground. And we have an output voltage from this node down to ground. So it's a common reference for everything. It doesn't have to be a ground. That location is the circuit ground, we might say, but often it will be ground there, but not always. And the goal in trying to solve something like this, well, there's several things we usually want to find. I'll get to that in a bit. We usually want to find the input resistance of an amplifier. We usually want to find the output resistance of an amplifier, and we want to find the gain of the amplifier. And we could look at just the gain of the amplifier, or we could look at the gain with a load back to the input of the amplifier, or we could look at the gain of the entire system from the output all the way back to the signal generator. And we do various combinations of those things, but finding gain is one of those principal things we want to do. Finding gain, input resistance, and output resistance are what occupies a lot of effort. And to find the gain, what we want is we want an equation for V naught or V out in terms of everything over here on the other side, which is all related to Vs. It may become Vi, things like that, but we want some equation V out in terms of Vs. So, and the way to find that is break it apart. First, we can find what Vi is, and that's just a divider. And then once we know that, we can also find what V out is, and that's just a divider from this amplifier, so this divider right here, and Vi is contained in this amplifier, so then we can substitute this relation in for that. And then we get an equation for V out on the left side with Vs or Vi on the right side. So Vi is just a divider, and it's Ri divided by Ri plus Rs times Vs. And V out is also a divider, and in the same way, it's RL, the load, over RL plus R out times this voltage source here, and the voltage on this voltage source is this gain AV naught times VI. And then we can substitute in the value of VI that we have here, substitute that into there, and we get one long equation. And it's not always this long. Sometimes different terms are or are not there, depending on what's going on. Or let's see, that times AV naught times this term, so the VI, so we'll put that in, RI over RI plus RS times VS. So now we have an equation where all of this is multiplying VS, and this is on the right side, and we have V out on the left side. So that's usually what you're trying to do, is you're trying to formulate, you have to rearrange stuff, you move stuff around, you do the substitutions, and you want to have this form where output is on one side of the equal sign and input is on the other side of the equal sign. Does that make sense? It's just an equation, we got all the terms, and we have it written in a way that we can do division. So then we can say that gain is equal to V out over Vs, which now is equal to RL over RL plus R naught times AV naught times RI over RI plus RS. And you can see if you look up here, if Ri is small compared to Rs, then Vi will be small compared to Vs. So that's saying if Ri is small compared to Rs, we have a small number divided by a big number. That's a fraction, which means that Vi would be much smaller than Vs, and that would affect the overall gain. That input divider would be important. And in a similar, sorry, this one over here. And in a similar way, if RL is as much as infinity, then we have infinity divided by infinity, and the gain just reduces to that, and that's a maximum. Otherwise, the smaller RL gets, the smaller our overall load will be compared to R out. So we'd like to have a big R naught, a big R out, although RL could be infinity. So a good voltage amplifier, this is a voltage amplifier, a good voltage amplifier will have a very big input resistance. And an MOS transistor, Ri is equal to infinity at low frequencies. So it makes a good voltage amplifier. Among other things. So MOS transistors, which most modern transistors are, with that very high input resistance, up here, that naturally makes for a very good voltage amplifier, no matter what kind of gain we have here. Bipolar junction transistors can also have a very high input resistance, and so they can make good voltage amplifiers too. So we would like the output resistance to be as close to 0 as we can. So if this is very small, ideally it's a short, right? If the output resistance is a short, then we send all of this voltage source here, AV not VI, it all goes to the output voltage if our out is a short. We want Ri to be high, call it big, and our out small for a good voltage amplifier. That's the kind of system that we would like to have. So this thing here, AV naught, or the open circuit voltage gain, is the amplifier without a signal source, so without this, and without a load, with the load being infinite, then we can find AV naught. So in that case, we just have we'd have a gain factor that we can find AV, and we could solve this V out over that. So AV is a voltage gain, and if it's AV naught, it's the open circuit voltage gain. So the voltage gain of this amplifier would be AV naught.
Open circuit voltage gain.
Right. So AV naught would be V out over VI, which would be just this this factor here. Oops, I guess I should call that AV naught. Call it right there, because we will get all with an open circuit load. We'll get all of V out will be exactly this. It's AV naught times VI. That's going to make more sense later on. So right now it's just a matter of getting the terms down and understanding what's happening. But as we make amplifiers, that'll be perfectly reasonable. So gain is a very important thing. It isn't always a huge number. It doesn't have to be a huge number. And there's plenty of cases where it's not a huge number. It's sometimes a fraction, and sometimes there's attenuation. Sometimes it's expected, and that's what we want. Other times, we just have to deal with it. At high frequencies, at a high enough frequency, we always get the place where we will have the situation where gain will become 1 volt per volt, or 0 dB, because 20 log of 1 is equal to 0. Well, in a real system, it's not a short, it's not 0. So the input resistance can be infinite for an MOS transistor, but the output resistance is never 0 for BJTs or MOS transistors or any others. There's always some output resistance. Although in the lab, sometimes it appears as if there isn't any. Some transistors are made with an ancient, remarkable technology where it might actually seem that way. But modern transistors are way, way far from it. Yeah, there will be some frequency. So at some very high frequency, at some high frequency, we call it the 0 dB frequency, or we have some other names for it, resonant frequency and some other things. The gain will actually be 1, and at even higher frequencies, it'll be a fraction. So you should realize that amplifiers can be cascaded. If we have a gain of 10 on one amplifier, and we go into another stage with another amplifier of 10, if this is this is called stage 1 and stage 2. This would be V out of 1. This would be V in of 2. This would be V out of 2. And so the gain here, V out 1 over V in 1 is equal to 10. And the gain here, V out 2 over V in 2 is equal to 10. But the gain from V out 2 over V out 1 would be 10 times 10, or 100. And if we looked at that in dB, a gain of 10 in dB is 20, so it'd be 20 plus 20 equals 40 dB. And we could keep adding stages. And every time we add a stage, the gain from here all the way back to here is just the product of these individual gains. And from here, you just multiply one more. Or if you're doing it in dB, you add them, because dB turns multiplication into addition. Does that seem okay? Any questions about that? So we'll talk a lot more about the details of that later in this course, and even more in electronics too. But fundamentally, at a high frequency, things are happening. As frequency increases, things happen more and more quickly, right? And at some point, you reach a point where the transistor can't respond quickly enough, and it can't. It can no longer do things as quick as we want it to, and so it can't have a perfect gain forever. And some of what limits the speed of the transistor are the resistances and capacitances in it, and those resistances and capacitances we can sometimes we can lump those all together into a single equivalent resistance and a single equivalent capacitance. And if we can lump them all together, then it's like a single time constant circuit, and it'll be like a low pass filter. And so at a high enough frequency, even if the transistor could respond, that response is filtered by that RC time constant. So that's a voltage amplifier. If I leave off the signal source and the load, we just have I'm always leaving off R0, the output resistance. There's a lot of tapping I got to do on this thing. That's fundamentally a voltage amplifier. We take a input voltage, and somehow magically this input voltage, that information comes over to this voltage controlled voltage source, and we multiply that input voltage by some number, AV naught, the open circuit voltage gain, and that creates a voltage, which then comes to the output. So this system has an input voltage, and it has a input or output voltage. But keep in mind, it really does have an input current, and it really does have an output current as well. So we can certainly find those. Now, if we transform the output to Norton, so we can take this output and just as easily transform this to a we can transfer either of these to other sources. So if we